Our final project for CIS 563 physically based animation is to build an explosion simulation system. Explosions are very impressive special effects which are commonly used in many video games and feature films. However, explosions are extremely dangerous in real life, making computer graphics necessary to generate these effects. The goal of this project is to build a system to create realistic virtual explosions. A semi-Lagrangian fluid system was used as the base framework. The system is controlled by the Navier-Stokes equation and includes buoyancy and vorticity confinement forces. It uses RK2 integration, cubic interpolation, and a modified incomplete Cholesky preconditioner. The implementation is based on the paper titled Animating Suspended Particle Explosions by Feldman et al. This paper discusses an explosion framework where the fluid is combined with the particle system, leading to complex interactions. Development of the explosion system based on this approach began with the smoke framework and then added a particle system, implemented the combustion model, and modified the fluid. All particles in the system have a position, velocity, and mass. There are two types of particles: fuel, which has a temperature and an ignition threshold, and soot, which has a lifespan. The particles' position and velocity are updated by a drag force, which moves them along with the fluid as it dissipates in the grid. The temperature is updated based on the heat transfer from the fluid.
The particle and fluid systems also have complex interactions within the combustion model. When a particle's temperature reaches a certain threshold, it ignites and begins burning. At this point, a portion of its mass is consumed and both heat and gaseous products are generated. A soot particle is also created at each time step while fuel is burning. Finally, the fluid is modified to only be incompressible when no particles are present. This allows for particles to influence the divergence field of the fluid, producing the rapid gas expansion effect seen in an explosion. The standard fluid temperature advection equation is also modified to include additional terms, which account for radiative heat loss into the environment and diffusive transfer of heat between the particles and the fluid. The explosion system is originally rendered using OpenGL and is written in C++. The simulation data was also connected to a Maya node for higher quality rendering. The code framework for the system is the smoke simulation assignment from earlier in the semester. The explosions were originally rendered using OpenGL, and each particle was captured individually. The particle position data was then used to modify the density field of the fluid, giving the explosions a much smoother and fuller appearance. Finally, this density field was transferred into Maya through a custom fluid emitter node for higher quality rendered images using Mental Ray. We now present some of our results.